You're playing it on your phone. Everyone's playing it. Shall we just have a little respectful pause? Okay, no, don't watch it now, please. Watch it at home with your friends and family. Because we need to move on. Have you noticed, it's interesting how it's very hard to bring things back from the internet.
Yeah.
So be very, very careful what you post. I mean, I'm sure actually it's quite good and it's not actually bad for Jarrah, but I'm just thinking, occasionally some of my tutors 5 years ago posted, not the tutors I've got now, but tutors I've had in the past have posted dumb things when they've been high school students, dumb things about their programming skills or something like that. And then they're tutoring people, and then the people look up their tutor and then they find dumb things they said. I'm just thinking, oh, this is the beginning of a whole new thing. So I think there should be a general amnesty in everything you said before. Every decade, everything you've said in the previous decade gets wiped. In fact, good grief. In fact, this reminds me of an interesting phenomena that I used to think about when I was younger. And I did briefly chat about this with Kitten. Do you notice that as you get older, you change into a different person? I noticed this when I was about 14. I suddenly thought, wow, me that was 8 was quite different to me that's 14. And I knew it because I remembered me that was 8 thinking, I never want to like girls, it's ridiculous and stupid and stops you thinking of interesting things. And you act like an idiot. And then me at 8 thought, but I know I'm going to like them anyway, even though I know that I've decided now it's stupid. Oh, that's so unfair. And then me at 14 was looking back going, oh, me at 8, you were so young. And so it was interesting at that time to suddenly think that really me at 8 and me at 14 were different people. And I wondered, wow, how can I be different people? And as I grow older, I keep being a different person all the time. And so I became interested in this and I started to think about it. And I started doing some observations. I noticed that the rate at which I became a new person started to slow down. And I invented an experiment to determine what the rate was, and you'll like this, Joe. It's when I thought of things that I'd done previously that embarrassed me. I thought of something really stupid I did, say, when I was 11. And if I thought, ha ha ha, that guy was an idiot, that was a different person. And if I thought, oh, it was still me. And I noticed as I got older, I could be embarrassed for longer and longer periods of time. So the rate at which I was changing was slowing down. I spoke about this, though not mentioning that example, in the graduation address I gave. I encouraged the students to continue to change. I think as you get older, we start to crystallize. It's like the temperature's going down and you suddenly freeze and you just like that music and you never hear new music ever again. And you read that newspaper and you never read another newspaper. And you decide you like this and that's never going to be changed. And you stop thinking about big questions and start thinking about small questions because the big questions have crystallized and you're only just hill climbing, adding little incremental bits. And if I think how much I've changed this semester versus how much you've changed, the biggest change I've made, I reckon, is that in my diary now I've decided to use a 2B pencil in honour of this course rather than an HB. And I've actually changed all my pencils to 2B. That's my change. But maybe some of you have started a journal and never had one before. Maybe you've completely revolutionised your idea about how to design and about decentralisation of control or whatever, or whatever, or whatever. That's fantastic. And I noticed to my sorrow as I grow older, I change my mind less and less often. And my encouragement to the graduates was to continue to change their mind and to continue to expose themselves to new ideas. And the example I gave was, I have a rule that when I listen to the radio, I must every week listen to, even briefly, a radio station that I wouldn't normally listen to. I'm compelled, last week I listened to, who's that really stupid, obnoxious guy? Kyle Sandilands. And I forced myself to listen to that whole show. Even I wanted to wash myself. And he was very stupid, but funny, actually. And then I forced myself to listen to Alan Jones and John Laws, and I forced myself to listen to Philip Adams, and I forced myself to listen to Triple J, and I forced myself to listen to Triple M, and I forced myself to listen to Radio National, and I forced myself to listen to the Muslim radio station that's near me, and I can't understand any of what they say, but they have this crazy music which sounds horrible to me, and I forced myself to listen to it. And my idea is, if I just go round listening to the music I already know I like, and hearing the people that I already agree with saying their opinions on the radio station populated by people I already agree with, I'll never change. And I want to make sure I keep changing all my life. So I think it's really important to constantly expose yourself to ideas rather than shutting them in. And I think you could sort of think of life as this annealing process. And I think the idea is reduce the temperature very, very slowly, please. I don't want you to crystallize early and suddenly make up all your mind. You know what would make me really happy? It makes me incredibly overjoyed when I change my mind about something really important. And I used to do that a lot when I was at uni. I changed my ideas about left and right ring, religion and non-religion, feminism, and I changed my ideas about compassion, and I changed my ideas about meritocracy and dictatorships and benevolent. I changed all these ideas several times, this way and that way. And then recently, I've noticed I don't change my minds that often. I have changed it about a few things recently, but not many, and nothing big. And I think that's bad. It just really means my brain's ossifying. I'm fossilizing. I'm turning into a rock. And I don't want you to do that. So one thing that would make me very, very happy is if when you were 25, say, you changed your mind about something. That would be awesome. And if you change your mind when you were 30, send me a postcard and it will make my teacher's day forever. If you send me a postcard and I think, someone changed their mind when they were 30. And I don't just mean change your mind about whether you like this movie or that movie. I mean, I've decided I want to be a Buddhist, or I've decided no more Buddhism, or whatever. Or I've decided this or that. I think changing your mind's a fantastic thing. And unfortunately, in simulated annealing, which is the technique we're about to look at now, there's a lot of exciting change early on, but towards the end, as the clock draws to a close, we have to start hill climbing because there's no more time to look around. We just have to do the best we can with what we've got. And there's a beautiful poem about that, which I remember. It goes something like, at 20 we do this, at 30 we do this, and I think it goes, at 40 we start to sadly shut the doors to the rooms that we know we'll never have time to visit. Oh, isn't that sad? No way. And I read Sir Gustav Nossel once. I heard him being interviewed. He's a brilliant Australian, as you know, incredibly old. And it was on a radio show and they were playing some music. And they said, and the announcer said, we normally get the guest to pick the music, but I picked this song. But it's a special song, isn't it, Sir Gustav? And he goes, I think it was Sir Gustav Nossel. Could have been someone else. And he said, yeah. And the announcer said, tell us why it's a special song. And he said, well, I like that song. He said, no, go on, tell us. He said, okay, it's me playing the violin. I'm playing that song. It's me, I'm playing the song. And the announcer says, because he's an incredibly modest man, and the announcer says, yeah, but tell us the story behind it. And he said, well, it's not much really. It's just, well, I was 70, and my friend said, you're too old to learn a musical instrument. But I gave it a go anyway, and I'm glad I did. And he was like 80-something at this stage. And he'd started learning a musical instrument at 70, and now he could play the violin awesomely, and he was 80-something. I thought, wow, that's a lesson to never freeze or fossilize or form into a big crystal, but to keep changing forever, because you never should shut those doors. Stupid poem. Okay, so we're now going to talk about this trick called simulated annealing, and it's particularly awesome. I love it. It's my favorite, although it's not a very fashionable programming technique. It's sort of, there was original work back in the 50s, and then in the 80s, in its current incarnation of simulated annealing, that's when it sort of appeared. There's a bit of publications around the 80s and a little bit of stuff in the 90s, but it doesn't seem to be a very popular strategy, but I love it more than everything else. I love it more than genetic algorithms. I love it more than neural networks. I love it. It's fantastic. I use it all the time myself when I have to solve large problems that are too complex to solve, when they're NP-complete problems and you'd otherwise give up. And over the years of me teaching algorithms and running courses, if I'm running in a competition with you guys and we need an optimized solution, so we're finding the best strategy or the best player or the best this, and we just want to get the best we can so we can beat everyone else, and we know that it's too big to look at all possible strategies, so we can't possibly find the perfect player, we just got to beat the other people. If I ever put a solution in and it wins, it's because I've used simulated annealing. Simulated annealing is my strategy of choice. And if you go on to do the AI courses, and we love AI at this uni, we do heaps and heaps of AI at CSE, AI courses are really all about this. They're all about, given a really large problem that's too hard to solve, come up with a reasonable way of coming up with a reasonable answer that's reasonably good. And you'll learn a whole range of techniques, including the aforementioned neural nets and genetic algorithms and evolution, various forms of evolutionary programming. And do we teach simulated annealing? Does anyone do AI? Yeah. Do we do it? Sort of.
You can apply it to things like reinforcement learning.
Yeah, you can. That's right. You can. But so they do teach it. But it's not very fashionable, would you say? But I love it completely. It makes my toes curl. It's so cool. So let's look at simulated annealing. It's the heuristic algorithm I'm going to be teaching you, because I wanted to show you one of the algorithms from this box down the bottom that I've just rubbed out of algorithms related to using the relationship between different solution states to converge on a better solution. Simulated annealing. Here's how it works. Here's how it works in general, and then we'll do it as a sort of an algorithm. You keep track of one state at a time, of one possible solution at a time. You evaluate that solution to see how good it is. Its goodness, D. You then pick a random neighbour. Well, it doesn't have to be a random neighbour. Let's say it's random. You pick a neighbour to that state. Now, neighbour is in this sense that when I was doing the hill climbing before, I meant I tried here next, or I tried here, or I tried here. It's not neighbour. The wheel nut thing isn't neighbour. So the idea is you find a solution which in some sense is close to the solution you've got. And it's really important that it be close in the same sense that the cost function or the profit function is continuous. So in other words, you expect, if this is near that, that the cost should be reasonably related to that in some way. Now there could be discontinuities. It could be you can move from one solution to one near it and suddenly everything's completely different. And that can happen occasionally and that's fine. But you don't want it to be the case that that's a regular thing, that the world is a pipe organ. Yep. You basically want everything to be reasonably smooth in this sense. So you try one solution, you work out how good it is. You pick a neighbour and you work out how good it is. Oh, and you keep track of the current one. So you say, the current one is D. I'm currently at state D. I'm going to consider D dash and see how good that is, how high that is. Is it higher or is it lower? Now, I'm going to have a rule that tells me whether I accept it, whether I move to D dash and just repeat the process, or whether I reject it and stay at D and find another neighbour of D. If I had the rule accept whenever things get better and reject whenever things get worse, what algorithm have I got? I've got a hill climber. I've got a, I'm not getting rid of this girlfriend until a better one comes along, sort of thing. Now the problem with that is, why don't we use that as our decision procedure to work out whether to accept or reject? Because of the problem of local maximum. The problem that sometimes to get from where you are to another solution, you might have to move through some bad lands of bad solutions. And if you're so averse to ever moving through anything bad, and you just take the safe thing and just stay where you are, because a little badness is no good, then you'll never find the wonderful place that you have to go down a little ditch to find. So if you're more adventurous, you'd accept the change even if it was worse. So in simulated annealing, what you do is you have an acceptance function that tells you whether you accept or not. And what it is you say the probability of me accepting is equal to something like, well, this is what the crystals use. This is what happens in annealing, if you know anything about crystals and annealing, which is the probability is e to the negative delta d on t. And there's a constant there which is called Boltzmann's constant or something like that. Does anyone know about this? Boltzmann's constant? You know about it? Is it called Boltzmann's constant? Yes. And it does talk about what? It talks about particles moving from one state to another in an underlying temperature environment. Yep. Okay. The likelihood of particles moving from one state to another in a given temperature regime, in a given temperature. T is the current temperature. So, as the temperature gets higher, this gets smaller. It's a negative thing, so it's a reciprocal. So as the temperature gets higher, let me just work it out. As the temperature gets higher, am I a little more likely to accept or more likely to reject? This is the probability of accepting. Does the probability of accepting go up as the temperature gets higher or down? It does go up, that's right. You had to do two tricky things. You had to divide and then you had to minus and work out what that all meant. And I hope you're able to work that out. So as t gets bigger, the probability of accepting gets higher. And as t gets smaller, the probability of accepting gets lower. Now the normal rule for a simulated annealing acceptance function is something like, it doesn't have to be this, but this is the bog standard way of doing it. If delta D is good, if we're getting better, accept. And if delta D is bad, we're moving to a worse state, accept with probability So how your program would work literally is you'd have some sample solution you're trying, you'd work out how good it is, Maybe what problem we're trying to solve. What's an MP complete problem you guys know really well? What's that? Knapsack. Okay. For a given amount of weight in the knapsack, what's the most profit you can fit in? So the thing we're calculating here, the D, is the amount of profit in it. So we try one particular random packing of the knapsack and we compute its profit. That's our current state and our current profit, D. And then we consider a neighbouring state. Well, what's a neighbouring state for the knapsack problem? Change it a little bit. How do we change the solution a little bit? Take something out and put another one in. Now, what's the problem? That is right. That will give us an adjacent solution. Why aren't I 100% happy with that? Because we've got an invariant now. What's the invariant? We'll always have the same number of things in the bag. So if you start off with 7 things in the bag and you just follow this neighbourhood function, you'll reach all other combinations of 7 things. But it's actually really important that we are able to, using our neighbour function, visit every single state. No, we'll never be able to visit every single state. It's NP complete, there's too many of them. It's important that we must be able to visit any state. Okay, so we've got to be able to get to packings that have more than 7. So maybe it's take something out, maybe it's swap, maybe we toss a coin, and if it's heads, we swap something with something else, and if it's tails, then we toss another coin, and if it's heads, we put something else in, and if it's tails, we take something out. So now we've got something that increases the amount in the bag, that decreases the amount in the bag, and changes 2 things in the bag. In fact, now I think about it, maybe we don't even need the swap function. Maybe we just need to take something in and put something out. Maybe that's our neighbourhood function. Yeah. I don't know. You'd have to try different ones and see which one behave the same, because you want, as you move to neighbours, the cost not to change too much. So maybe in a particular instance of the problem, swapping changes the cost less. You want that to be a relatively smooth thing. Okay. So that's our neighbourhood function. Maybe we decide we'll add another thing to the bag. And we see, is it better or is it worse? And if it's better, or maybe we do a swap. Let's say a swap, because it's clearer than what better and worse means. If you add something to the bag, better means, well, it's naturally, unless objects have negative value to you, adding more to the bag will make it better, unless no, I mean, unless you go over the weight of the bag. That's the only way that adding something to the bag could actually be negative, is you exceed the weight. So then we'd have to have some penalty for going over. It's a bit more fiddly. We'll have to come up with arbitrary constants. Oh, the goodness of this solution is this if the bag's a proper packing, but if the bag goes over, it's something else. Yeah, well, actually, let's try and come up with a good profit for the bag. What's the profit of a packing for the knapsack? We could say equals the sum of the values. Let's say sum of values equals V. We'll say it's equal to the V if V is less than or equal to V max, if sum of the weights. That's the problem, isn't it? So the value, not the probability of a packing, the value of a packing is the V, which okay, I think we're reasonably close to having something that makes sense now. The value of a packing of a knapsack is V, the sum of all the values, if the sum of the weights is less than or equal to W max, equals, what if we're over the weight? What's a good value function to give it? What value function would you be inclined to give it? How would you assess the value of a knapsack that was too full? You could say it's -1, but then it's going to regard all overfull knapsacks as utterly terrible. And also you've introduced a discontinuity. You're not making the weights of neighbours really near each other. Now maybe that's appropriate, but I'd be inclined to go for more smoothness. I'd be inclined to say something like, can someone think of something that's more smooth? Yeah. No, it could be any number of objects in the knapsack.
Well, if you've got heaps and you've just gone over, that means you've got lots of room to adjust it.
Yes.
But if you've only got a few items and you've gone over,
yes,
that means that there's probably not a good solution because you've gone
Oh yes, but no, you've got to give me a number as a problem. I need to know a number. This is the thing you can't ever do with actual real girlfriends. You actually need to say, our relationship was 6.9. Or something like that. Yeah. Okay, so you could say the number of objects in it is part of the cost. You could say V equals the number of objects. Okay, you could say something like the packing is V if the weight is under the limit, or it's a number of objects if the weight is over the limit. And that way, if it's over the limit, you'd prefer packings which have more objects in them because you've got more scope for pulling things out and bring it under. Yep, that's a reasonable one. Yep, I like that.
How about you like bounce off the top? So like
Yeah, that's what I was thinking, but I like your idea too. So,
the number just goes down again.
yeah, equals
Total weight minus object weight.
V times, some scale of V by how much you're over. So if you're 20% over, only take 80% of V or something like that. Yeah. Times the total weights, minus the weight max over the total weights you've got, or something like that. Scale it some way. So if you're just slightly over, then the value slightly goes down. So it's not killing you for going overweight. Yeah, if you're only supposed to put 10 kilograms in the knapsack and you put 11 kilograms in, it doesn't kill you for doing that, but it says the value of that packing is only 90% of the value of the objects in the bag. Is that 90%? No, 10 on 11 of times the value of the objects in the bag. Yep, that's a reasonably smooth function. The thing about simulated annealing is you never know what's going to work. So what you do is you have to actually tweak it. There's no actual solution we can give you that will work in all cases. You get a simulated annealing problem and you start to think, okay, what's my neighborhood function? And then you think, okay, what's my cost function? And then the last thing you think is, okay, what's my acceptance probability? And if you can't think of anything, you just stick this in mindlessly and gee, it works for nature, so it'll work reasonably well for us. But you often have to put a constant in, K, to sort of normalise it a bit. So they're the three components, I guess. And your start state that you start from. Pick a random state for your start state, so we probably don't have to talk too much about that. So your acceptance function, your valuing function, and your acceptance function, your valuing function, and your neighbourhood function. Your idea of how to pick a random neighbour and what you need. So how a simulated annealing works in practice is at the beginning, you set the temperature. Oh, there's one last thing. What's the temperature of the system? Initially, you set the temperature really high. And remember, high means the probability of accept is really high. And the probability of accept is what you look at if you see a solution that's worse than where you are now. So what that means is, in the early stages, you're going, oh, that's worse than where I am now. Will I go there or not? I'll roll the dice and see if I do or not. And if the probability of acceptance is high, you go, okay, I will go there anyway, even though it's a bit worse. So early on, you're not risk averse. You take lots of exploratory steps. And even if you're moving to worse places, you're happy to do it. You're not completely happy to do it. The worse they get, the lower the probability that you'll accept them. So if from here there's a big drop in goodness, and if I go this way there's a small drop in goodness, the chance that I'll accept here is actually much lower than the chance that I'll accept here. But there's still a non-zero chance I'm going to accept. So eventually you will be able to wander around everywhere through you can reach any point in the solution space, and you wander around. And when the temperature's high in the early days, you wander around like crazy. And then over time, the system slowly pulls the temperature down. And as it pulls the temperature down, you're less and less likely to take risks. So if this is a big drop going that way, I'm just not going to do it at low temperatures. The chance of me doing it, the probability is so low, it's unlikely that I'll throw the dice and be able to do it. But if it's only a small change going down, I might still do it at reasonably low temperatures. But then as the temperature goes even lower, no, I'm not even taking a small change. And when the temperature gets right down to the bottom, all you do is hill climb. So here's how you do a simulated annealing algorithm. Here's how you write the program. Here is the program in pseudocode. Oh, no, there's some people. There's some people. And you say, guys, I think we should use simulated annealing to solve this problem. And they go, oh, cool, man, that's fantastic, yay! And this guy goes, I love simulated annealing. It's so easy and it gives me fantastic solutions. And these guys go, I don't know what you're talking about. I didn't pay attention in that lecture. I'm sad. I'm sad. I'm sad. And this guy's asleep. So that's the story of being a teacher. He's only got one eye. Okay. So here's our simulated annealing algorithm. It goes like this. Pick start state. Pick a sample solution. I don't know, stick some random things in the knapsack and say that's my solution. We'll call current equals start. I don't even know why I had start. So we're going to have a current state, and the current state's going to have a value, how good it is. And we're going to say candidate equals random neighbor of current. Does that make sense? So we pick a random neighbor of where we currently are. And then we're going to say if except current equals candidate, otherwise do nothing. And then we're going to iterate that some number of times. How many times? Well, what's your time budget? I don't know. Let's just say it's 1,000 times. It could be 1,000,000 times. Depends how expensive it is to do this stuff. And of course, all the obvious things, we're soon going to come along and say, look at what is a good accept function, what's a good neighbour function, and so on. But you can see straight away, if this is something that's going to involve lots and lots of simulations, we're going to want our accept function to be reasonably, what? What's one property accept's going to be if we're going to be running it a bazillion times? Fast. We need it to be cheap to compute. And similarly, the random neighbour has to be cheap to compute. These things all have to be reasonably good. You can come up with very, very fancy ones that you think, oh, this will give me slightly better things. And I often find when I put that in, I actually get a worse solution because I'm able to run many, many less simulations. But sometimes I get a better solution. So with simulated annealing, you're always running it, testing it, watching, observing it, think how can I do it better, tweaking it and running it again. And you normally spend a day or something tuning the damn thing. But once you've got it tuned for that problem, it runs like anything and it just finds fantastic solutions. Okay, so you loop this 1,000 times. After you've looped it 1,000 times, we'll assume we're in equilibrium. You've reached somewhere reasonably good for that temperature and you've been adventurous and wandering around. Then what do? Then we go decrease temperature. Decrease T. And remember our acceptance function is going to have T in it as a variable and as a component. And as you reduce T, it reduces the chance of accepting anything that's bad. Decrease T and start again. So we've got a double loop here. And you keep decreasing T until T is at min. And then you stop. Return current. I don't think stop is a function, is it? There we go. Okay, how's that? Does that make sense to everyone? That is simulated annealing. It is absolutely beautiful. Hit me with some questions, because I've been talking a lot and you haven't been saying anything.
Why isn't it popular?
Why isn't it popular? I don't know. I don't know why it's not popular. Maybe because it's just random guesses from each other. Maybe because it does need a lot of tweaking to make it good. So it's very hard to tell someone how to do a simulated annealing algorithm, them go away and implement it straight away and it be good. You normally spend a fair bit going, I might just change my neighbour function slightly. No, neighbour's normally fairly straightforward. I might just change my cost function slightly. Tweak it a bit here. I might change the temperature schedule, the rate at which you reduce the temperatures. I might change that slightly. And you have to tweak this and tweak that. It's a bit fiddly. It's a bit of an art. And you just fool around with it. I taught myself simulated annealing by picking a problem that I wanted to solve, which was routing Thomas the Tank Engine around a network. We had two trains and they had to pick up and drop off goods at various specified locations, but they were sharing a track and they could never collide. And we had to make instant routing decisions whenever they passed a signal point. And we didn't have full or complete information. And there was not enough time at the speed the damn thing was running to do much thinking at the time you make that decision at the junction. So we wanted everything to be pre-computed into a table. So when you got to a junction, you just looked up the table and it said, given the current values of all the signals and switches around the network, here's what I should do now. Turn this signal this way. Oh, sorry, turn this switch this way, turn this switch that way. So it was very fast to execute, but what were the appropriate values to fill in the table? So some people used intelligence and cleverness, my students that I gave this problem to. Some people did trial and error, and I wrote a simulated annealer. And I fooled around with it, and it took me maybe a whole weekend to get it working nicely. And I tried this value of distance and this value of next neighbour, and I tried this way of weighing it up, and then it was all taking too long, and I couldn't do enough loops. I thought, oh, I'll just simplify this thing, because I'll be able to run more values, even though it'll be... And I fooled and fiddled and diddled, and at the end of the weekend, it was just so awesome. It rocked everything out of sight, but it did take me a weekend of fiddling with it, and probably none of the things I did in making that one better are instantly applicable to any other problem. You'd have to start a new problem from afresh. But what I did get from that is applicable to other problems is this incredible surprise and delight that something so simple can give amazing solutions. So now I persevere when I've got a simulated annealer that's not quite working right. I fiddle and diddle and tweak it a bit till I make it good. Now, the guy that I talked about before, Steven Scienna, Yale guy, he uses simulated annealing and he really likes it. And there's a lot of crap about simulated annealing on the internet. It's simultaneously not very well used or commonly used, and it seems to me when it is used, it's not used very well. But if you read any of his stuff on simulated annealing, fantastic, fantastic. And he has some very, very clever things to say about possible acceptance function, possible the cost function. Where is it? Oh, the accept, it's not written here explicitly, is it? You accept based on the cost difference. He has some very clever ways of working out cost functions. For example, one problem he talks about is laying out chips on a circuit board, I think, and trying to minimize wire runs or something like that. And you have to lay all the chips down, then you work out the wire runs between them, and then you try a different configuration of chips and you have to work the wire runs out. And he found that once you've laid the chips on the board and they're all packed, it's actually quite hard to move the chips around the board, like jiggling them to get the next neighbour. If you were just doing it yourself, you had a whole lot of chips on the board and you just thought, oh, I'll try this instead, and you just want to make small changes, so you want to jiggle the chips around. But if the board's really packed, it's hard to actually move them around and you get stuck in one spot. And he said, so he realised he would allow it to have solutions where two chips were on top of each other. So you could slowly move a chip on top of each other. And instead of saying that's impossible and I'm going to penalise you $1 million if you come up with a solution that has chips on top of each other because we can't build it, so it's obviously a dumb solution, he said, I'll allow those illegal solutions and I'll just have a small penalty if they're illegal, if chips are on top of each other. But he made that small penalty related to the temperature. So as the temperature dropped, the penalty for having chips on top of each other started to grow. So in the early days, chips would just wander around the board and be on top of each other and things and look for reasonably good configurations. But as the temperature started to drop, they started to repel each other a bit. And at low temperatures, there was no way chips were going to move on top of each other. This is very, very clever. Do you agree? Very, very clever. Yeah. So that's possibly one reason why it's not popular. I don't know. Does anyone have a thought why it might not be popular? It's too good, it's a secret. The people that know don't tell other people because they want to keep their elite secret knowledge. Stephen Conroy. Oh, yeah. You mean the cool dude? Okay, all right. So how are we going? We've only got a few minutes left. Oh, we've got a few. I think probably the last thing I want to say about this is, for me, simulated annealing is a really nice summary of this issue that I've talked about a couple of times in the course, which is, you know, I was generally skeptical, although I'm impressed by how it works in practice, with this notion that very small incremental changes to designs can lead us to a brilliant design. Can you see, really, I'm thinking about it in the context of simulated annealing? I'm essentially thinking, if you make a small change to your design, and then you make another, this is the XP thing, okay? We just make small changes, one at a time, and we incrementally converge on a good design. I just sometimes think, maybe you need to do a leap. Maybe small incremental changes aren't good enough. That's just hill climbing. Maybe sometimes everything needs to be completely changed. And now in XP, they sort of take that into account. They say, you make a small change in terms of functionality, but maybe that results in a big change in code, and then you have to do all this refactoring to make all the code good. So they sort of hide the complexity in the refactoring step. And that's good. I like that. And I also like the fact that that then leads them to a whole lot of really good thoughts and recipes and guidance on how to do refactoring, which I find really useful. So I like all that. But I'm still always inclined to think that maybe incremental stuff is good, But maybe sometimes you need a revolution and a big change, a paradigm shift. Maybe you do. But then in history, whenever we look at a revolution, I don't know any good revolutions. They're all bad and they suck, don't they? It's a hard problem. So, so that's my dilemma. And this is sort of goes back to what you talked about a couple of weeks ago. Do you remember that, Theo? This idea of, do we want to just make small changes and build on the shoulders of giants, or do we want to have radical new ideas and jump around? And simulated annealing, I think, gives us the best of both worlds. At high temperatures, it jumps around and explores, like you guys now in your 20s are doing, but less than when you're in your teens, although you're probably in your teens, less than when you're in your 1 digits. And it will get less every decade, so hold on to that. Don't let the temperature drop too low. So anyway, I think that's very, very interesting. This difference between, can you incrementally converge on something, or do you need a paradigm shift? And I still don't know the general answer to that, but I think that's a question that seems to come up in every field that I look at. Yes?
You said that in human history, you had the huge leaps, the revolutions. You haven't seen any good ones.
Revolution, oh, I mean political revolutions.
Oh, okay.
Yeah. No, I mean ideas revolutions are always, for me, the big leaps. They're the amazing things. You know, my colleagues publish papers all the time, and publishing is all anyone cares about. But whenever I think of something to publish, I'm thinking, you know, projects I could do, the really safe ones are the ones where you take some process and say, I can make it 2% faster, or I can shave a little bit off here, I can make this small change. And I think, I don't really want to do that. Although I really like that other people do that, I would really like to do magnificent things. And my PhD student, Roland, who's just finishing now, and I'm so proud of, he'll be finished within 4 weeks. He set out, when he set out to do his PhD, he said he wanted to do something bold and big. And I said, man, that's risky because it might not work. I'm such a dad. And he said, I really want to do it. You know, it's what it's all about for me. And I said, I know it, because that was what my PhD was. I said, I know where you're coming from. I see what you're saying. Just be aware there's a risk. Okay, let's do it. So we held our breath and dived in. And for 2 years, he worked really hard on the problem. And it seemed that it wasn't going to be solvable. And we were just going to have nothing at the end, rather, you know, like your projects. No, rather, what I was saying about your projects was I didn't want you to do that with your projects. I wanted you to do this incremental thing every week, slowly adding functionality and converging on the solution. I didn't want you to hold back and then blurt out a fantastic solution at the very, very end, because I'm scared of the risks, because as a computer scientist and as a person that does security simultaneously, I see risks all the time and I see how they go terribly wrong. And I just am very risk averse. So this is a very risky strategy, the jumping around strategy. Yeah, it normally doesn't pay off. So that's why I'm so pleased that you guys hopefully all did this process of incrementally improving your code. But he didn't want to do that for his thesis. He wanted to do this big new idea that was quite revolutionary about elections and ways of doing elections that are quite beautiful online, that I think will have incredible value to the world if we can ever work out how to do it. And anyway, the exciting thing was, after 3 years, he finally got something. And he had this incredible breakthrough. And he had this brilliant thing, and it's so fantastic. And I'm so proud of him. And I look at all the other people getting PhDs, and they're not my students, so I'm prouder of Roland than anyone in the world. But a lot of them are doing these little PhDs, and good on them for doing it, and that's fantastic. And they finished. Wow, that's incredible. Good on them. I'm really impressed and moved that they were able to do that. But I'm just so proud of Roland because he's done a big thing. And I think, but that was risky. It might not have worked. So anyway, this is the big versus small. I never know what the solution is, but my favorite one is big when it works. Yeah, that's certainly good. Now, what I wanted to do was give everyone a piece of paper and have you write very, very quickly what you think, what was this course even about? It was computing. I'll give you a hint. Okay. What do you think my main objectives for the course were? What do you think I wanted you to do? How did I want you to change? What do I want you to know? Just write a couple of words, what you think, because this will help me work out how effectively I've actually done what I was hoping, or we've done what we were hoping that we could do. Does anyone need more?
We didn't know what a pen was anymore.
Yeah, yes, that's right. You need a pen. Do you want to just pass along? Pass along. Would you mind passing that along to everyone? Oh, there we go. I'm passing along too. And would you mind passing that across? I'll get some more for you guys. Yeah. Just scribble something down. And on your way out, if you could place it here. Does anyone need some? Okay. Do you need one? There you go.
I've been writing all lecture.
Oh, you've been writing all lecture. Oh, okay, cool. Thank you. Thanks, guys. Hang on, there's more coming. Just stop. Ah, there we go. Scarcity. Quite amazing. So they just asked people in a massive online survey, they just presented random colours to them. It's very funny. You should read the whole of the article. But he wrote it up very nicely. And he asked people to name the colour, and then he's plotted on, just these are the saturated colours, he's plotted what people called them. So it's, in a sense, quantifying something you'd think would be unquantifiable. Well, attempting to quantify. Yeah. Very funny. And if anyone wants to look at the rocks on the way out, you should. They're very beautiful. You don't get to see much granite in Sydney. Oh, unless your sink's made out of it, I guess. And I'm going to build a castle. I'm going to build this. I'm going to put this in my office to make it more old and wise. Oh, and one last thing I wanted to say. Scatty brain. This book, remember I told you about this book by Roger Zelezny? This is all the books put into one cover. I think he wrote this book up by just making it up as he goes along. And it's a really interesting story, but I reckon he just made it up as he went along. And towards the end, he gets in a bit of trouble because he's just hill climbing, essentially. And he doesn't really have, I don't think, an overall plot, though he tries to retrofit one to it. But it's such an awesome story that I love it. And it makes me think inventing stories as you go is the way to go. Small, incremental change, brilliant. And then this book by Just Before It is so awesome. This is clearly well thought out in advance. He's done a complete design up front. He hasn't done any sort of incremental design. And it is awesome too. I can't decide. Can't decide. Something well worth thinking about. Incremental, big design up front. If you could put your books down here, or if you haven't written a book, just a few words, down here on the table. Thank you very much, everyone.